My name is Amir Ali, and I'm a PhD student at Carnegie Mellon University. Today, I'm going to briefly describe our work at ISCA 2019, which is titled CoNDA, Efficient Cache Coherence Support for Near-Data Accelerators. Specialized accelerators are now everywhere, and they are widely used to improve the performance and energy efficiency of computing systems. At the same time, recent advancement in 3D stack technology has enabled near-data accelerators. These accelerators can further boost the benefit of conventional accelerators by moving computation closer to the data and reducing data movement. However, a major system challenge for adopting these accelerators is coherence. In fact, maintaining coherence between the NDAs and CPUs is very challenging because of two reasons. First, the cost of off-chip communication between the CPUs and NDAs is very high, and the second reason is that NDA applications have poor locality and generate a large number of coherence misses, which in turn lead to a large amount of off-chip coherence traffic. And because of these reasons, it's impractical to use traditional coherence protocols for NDA coherence. In this work, we extensively study three major approaches for NDA coherence: fine-grained, coarse-grained, and non-cacheable approach. And we make three key observations out of our analysis. First, we observe that these mechanisms eliminate a significant portion of NDA's benefits. And then when we dig deeper, we find that the majority of off-chip coherence traffic generated by these mechanisms is unnecessary. And finally, we find that a significant portion of this off-chip traffic can be eliminated if the coherence mechanism knows what part of the data will be accessed by the NDA. Based on these observations, we find that an optimistic approach to coherence can address the challenges related to the NDA coherence. We find that an optimistic execution model can enable us to gain insight into the memory accesses before we do any coherence checks. And then we can use those insights to perform only the necessary coherence requests. Based on that, we propose CoNDA, a coherence mechanism that lets an NDA optimistically execute the kernel and then use the insights during the optimistic mode to identify and avoid unnecessary coherence traffic. So let me show you a high-level overview of how CoNDA works. So the application is running on the CPU, and the CPU issues a call to offload the kernel to the NDA. While the NDA is working on the kernel, the CPU continues its execution in parallel. During the optimistic mode, the NDA assumes that it has the coherence permission for the entire data that it is accessing, and as a result, it does not send any off-chip coherence requests. At the same time, we tracks all of the memory accesses from NDA and CPU to the NDA data region during optimistic mode using compressed signatures. When the optimistic mode is done, we use those signatures to check if any coherence violation has happened. If we find that there was no coherence violations, we can commit the NDA data updates using the necessary coherence request and continue execution. If we find that there was a coherence violations, we use the signature information to resolve those violations and we re-execute the kernel. Our result shows that CoNDA consistently retains the benefits of NDA, and it comes within 10% and 4% of the performance and energy of an ideal NDA coherence mechanism with zero cost for coherence. Please refer to our paper for more detail on our work. Thank you so much.